Hey guys, George of Troglodyne, doing yet another team cast with my brother here. This time I want to talk about design patterns and why they're so important. In Perl, there's a concept that's been sort of popularized by Damian Conway of every problem can be solved with yet another abstraction layer. Well, this is very obviously true in pretty much every programming problem. And I've noticed sort of a nice thing about design patterns is that no matter what abstraction layer you operate at, and in general, the highest abstraction layer tends to win because of effects we'll go over later. And these design patterns, they work everywhere. The best example I can give you of this is things like pipelining in CPUs. Okay, basically all it's doing is we are splitting up a bunch of data, which is a big block of stuff across multiple execution units, right? Well, doesn't that sound a whole lot like actually forking a process and feeding the same data into multiple different things? It's just bone standard parallelization, or
Yeah,
say,
or even if you go as far as pub sub or some of the other like queuing methods,
yeah,
that sort of thing for
message
tasks.
queues are literally pipelines.
Yeah, yeah,
It's the same with if you go into the idea on a motherboard of a bus. That's going to be, well, let's make sure that we can get the things we need the most to the execution units we need the fastest, right? How do I get the data into the execution units very fast? How do I
yeah,
fill these pipelines as fast as we possibly can?
yeah.
Right?
And usually the answer is, well, more lanes, dummy.
Yeah, exactly. And that's why it's no surprise that SMP, superscalar architectures, all this kind of stuff has won the day in the sort of computer wars, shall we say. And it's a shame that the old design pattern that we had from the really early days of one thread, that's it, has persisted so long that we still write programs like they're C programs instead of, no, we're actually going to be writing scripts that are intending to be broken across pipelines.
Right, and that is more of a hack than anything else, which, I mean, considering the heritage of most programming being hackers, trying to just get the job done and wrap their mind around it in those early primitive days, it's certainly understandable why the whole single thread kind of mindset made a lot of sense.
But it also means that compiler authors had to do almost all the heavy lifting for you. It had to do all the work for you. And the days of that are sort of coming to an end because all this magic that used to be hidden and in the compiler, now you can more or less just directly embrace that design pattern and not have to do that kind of stuff. You can actually do these algorithms directly rather than worry about, did the compiler do the right thing? Am I giving it the right hints? It's less of a like I'm using this holy thing and I need to do the rituals in the right way.
I'm using Holy C.
Yes, exactly. When on the other hand, I just know that this is the design pattern that works at every layer of abstraction and I'm just embracing it. I think the things that embody that the best are these really highly distributed systems like, say, DigitalOcean or an AWS, or all these things that they've sort of standardized around the APIs that and the services that Amazon created first, and then everybody else has realized, well, we better do the same thing. But really, you look at the way that they're exposing these computing resources to people. They're giving you pipelines, they're giving you buses, they're giving you all these same things that you get out of a CPU, and
Well, and they're also giving you one of the key innovations that came along with the Industrial Revolution, which is standardized parts, which
yeah,
in this case is a standardized API.
which sort of gives me a little crystal ball as to like, so how are people going to access file systems in the future? How are people going to access storage? Well, they're going to access it like an S3 bucket because that's the abstraction layer that people are actually doing to do work at scale. So you might as well do it at the lower level too.
Yeah. Despite file system access itself being an abstraction as well, which is
Yeah,
kind of
it's
interesting too.
already an abstraction layer on top of usually a binary B plus tree, right?
Yeah.
Because that's what actually works for storing and retrieving large documents.
Well, certainly, if it's BTRFS, that's most certainly the case.
Oh yeah, but almost all of them use some kind of B tree of some format. I mean, there were some really early file systems that use things like a trie or whatever, but
Yep.
a binary tree is pretty much what you need for a file system. And it's the same with regard to SQL databases. They're just another file system nowadays when you really get down to it. It's the same with like software transactional memory. You're actually treating the memory as if it's yet another file system for you to deal with. It's just a volatile file system. So what I'm seeing is like everything is going to be abstracted into one way to talk to data, and then one way to give it to execution units, which again, doesn't this look like a big pipeline sending things into CPUs, you know?
Yeah.
And then it's just a choice as to, am I going to do superscalar, which is like I'm splitting it across multiple execution units, or am I doing like coroutines where it's, they call it temporal threading rather than hyper-threading, in that I am, jumping and executing one thread rather than, but essentially still only doing one execution process here.
Right, and you can see this pattern more than in just, say, AWS, some of the other hyperscalers out there. You can also see it in certain types of games. You can see it in just culture at large. Certainly the bus problem is something well known to anybody who's ridden on interstate highway systems.
Yes.
Or been involved with trying to design them as well, because generally there's only one answer whenever there's a congestion problem, and it's
add more lanes, because
well,
you need to increase the speed of the average packet of data going over there, also known as a car.
Yeah, and why a lot of designers have been very reluctant, I guess would be the very polite way to say it, about adding things like HOV lanes, toll lanes, things like that.
Because all they're doing is taking a lane out of the system.
Yeah, they understand that to have an optimal system, you in fact need to be adding lanes instead of subtracting lanes. And if you already have a congestion problem, you're just going to compound it worse.
And that at some level, you may even need to consider, rather than doing this atomized, lots of different little packets coming in, you might actually want to start shipping them in bulk and use a different protocol.
Right, which is where you see trains and subways and that sort of thing in some of the most densely packed metros become a thing, and why they became a thing even in the 30s, because they saw that key insight even back then.
Well, it's, yeah, you sort of compare the highway system with a train system. It's like the difference between TCP/IP talking, which is very, very robust and able to do communication even under unreliable links, which is like, that's sort of this exact problem that, cars and freeways are solving. A lot of people wanting to do a lot of things and no real reliable way of figuring out what it is, as opposed to a train. It's like, it's going one place and that's it.
And you know exactly what's going on there.
And so you can pack them in such ridiculous density that you can get a throughput and bandwidth that you can not imagine.
And never get anywhere else.
And so as the web, for example, has matured, we've started to realize that these patterns are at play. And so that's why people are saying, well, maybe we don't actually need to use TCP/IP for this. Maybe we should actually use something like HTTP3 is developing, where it's actually like UDP datagrams. And
yeah, right. And so long as they actually understand well enough what's going on, and like I was saying earlier with games, most games, their multiplayer is done over UDP, and for good reason, because they know exactly what the data is going to be and how it's going to be received. There's not going to be this element of chance, so to speak, whenever they're talking about packets this game is going to receive over this port. Yep. So in that case, yeah, it makes perfect sense, what we're going to be doing, and just discard every other data that doesn't match the whatever it is instead of TCP/IP. Where no, that's not a safe assumption at all. Yeah. But yeah, going back on to talking about games as well, we even see at the player level these sorts of concepts reflected, like say if you're playing a automation-based game like Factorio, something like that, where you're having to get resources from point A to point B. You see the same types of issues.
Yeah, doing that efficiently, there's only really the design patterns that you see everywhere else that you can rely on. You're going to need to build a bus to get all this stuff there. Yeah, you're going to need to pipeline it into execution units.
And if you don't have enough space to properly do it, things like, in fact, building trains seems to actually be a pretty efficient way of getting resources in certain constrained environments where they need to be.
Yeah, and that's really what we wanted to stress here is that uh, there is always a good solution that you can look for at any layer of abstraction, that you can draw inspiration from something that's a lower level. If you can't really think about, well, how can I get the performance I need? How can I get this thing executing on the level I need to? Well, I can guarantee you somebody at a lower level has figured it out already, and you probably just don't know it because it's been abstracted away from your ability to understand it. You know,
Yeah,
it's in a compiler or it's somewhere in the interpreter, and you can lean on that same exact technique to get you the kind of performance you need.
right. But just like the saying is, everything's already under the sun been done, something like that.
Yeah, it's as above, so below,
As
shall we
above,
say.
so
Yeah,
below,
yeah.
with regard to peeling this onion on tech. You can find all these patterns, whether it's in nature, whether it's in some of the other works of man that have come throughout history, for deciding all of these things. Like you can even see in blockchain technology now, you know, the proof of stake and some of the consensus based coins, well, they're using typical democratic forms that have existed since ancient Greece.
Yeah, I mean the consensus algorithms to solve the core problem of I believe they call it the Sybil attack, where it's a bunch of personalities, shall we say, that don't agree, on the
Mm-hmm.
network. It's all a design pattern that is very, very old,
That's why
and
it's named after Sybil.
so the big deal is that you know when you do that, you start to realize, well, it turns out there's some limitations to this tool. And when people do this exact same thing elsewhere in society and at other layers of abstraction, it tended to only be used for this thing. So it's a very useful heuristic for you to realize when somebody is actually, they're blowing smoke on you,
Yeah.
So uh, very much practical use can be gained for you by understanding these design patterns that exist at every single layer of the stack, every single layer of abstraction that you can think
Well,
of.
especially whenever you're trying to pitch something or talk, especially to people that aren't as technical about what you're
Or
doing.
that are familiar with a different layer of abstraction than the one that you're operating in.
Yeah, you can provide that familiar idiom to that person and explain what you're trying to explain in a much easier way.
And
Even
why
if
it
it
will
isn't
work.
a perfect one-to-one match, it can be a good enough bridge to get them where they need to be in their understanding of what you're trying to accomplish.
All right, hope you enjoyed the video. We will see you guys later.